Hello everyone. In this video, we are going to discuss the fundamental trigonometric identities. And at the end of the lesson, you are expected to determine whether an equation is an identity or a conditional equation and apply trigonometric identities to find other trigonometric values. Okay, so to start, let us first consider this activity. So in this activity, we are going to consider the following expressions and determine its domain. So we have here four expressions involving the variable x. And since we are going to look for the domain of the given expressions here, we are just going to find the real values of x that will make the expressions defined in the set of real numbers. Again, since we are going to find the domain of the given expressions here, we are just going to look for the real values of x that will make the expressions defined in the set of the real numbers. Okay? So first, let's consider 2x plus 1. Now take note, if we are going to substitute any real number to the expression here, so any real number x to the expression, the value will still be a real number, right? Like if we have x equal to 1, so we will have 2 times 1 plus 1, that is equal to 3, which is a real number. Suppose we have x equal to 1 half, that will become 2 times 1 half plus 1, and that is equal to 2, which is still a real number. Okay? And observe that if you are going to substitute any real number to the expression 2x plus 1, the answer will still be a real number. Thus, the domain of this function is the set of real numbers. So x here is an element of the set of real numbers. Okay? Now, for number 2, we have the expression the square root of x squared minus 1. Now, take note, whenever we have square roots, that expression will only be defined if the radicand is greater than or equal to 0. Since the square root of a negative real number is imaginary, which is not a real number, right? So therefore, we must restrict the values of x here such that the radicand here, which is x squared minus 1, is greater than or equal to 0. Thus, we will have x squared minus 1 greater than or equal to 0, right? Now, it will follow that x squared is greater than or equal to positive 1. Okay, now taking the square roots of both sides, okay, so extracting the square root here and also here, this will become square root of x squared is just absolute value of x, right? Greater than or equal to square root of 1 will be positive 1. Okay? And absolute value of x greater than or equal to 1 means that x is less than or equal to negative 1, or x is greater than or equal to positive 1. Thus, the domain of this function is the interval, okay? Um, the union of these two intervals, negative infinity to 1 inclusive, and 1 inclusive to positive infinity. Okay, so this is now the domain of this expression. Okay, now for the third expression, we have x over x squared minus 3x minus 4. This is a rational expression. Take note, this will be defined if the denominator will not be equal to 0. Okay, so those values that will make the denominator 0 are not included in the domain of the expression. Okay, so to find that value, we will just equate the denominator to 0. So we will have x squared minus 3x minus 4 equal to 0. And from that, take note x squared minus 3x minus 4 is just equal to the product of the factors x minus 4 and x plus 1, right? And that it will be equal to 0. So from that, we have x minus 4 equal to 0, thus x is equal to 4, and x plus 1 equal to 0, so we have x equal to negative 1. So therefore, 4 and negative 1 are not included in the domain of this expression. Thus, the domain will be the set of all x element of real numbers such that x is not equal to 4 and negative 1. Okay? And for the last one, we have x over the square root of x minus 1. Take note, this one will be defined only if the denominator is not 0, okay? And the value of the radicand is greater than or equal to 0, okay? But if the radicand here is 0, so we will have square root of 0, so that is just 0. So that will not be included since that one is in the denominator, right? So in this case, we will not include those values that will make the denominator 0. So we will just have x minus 1 greater than 0. So we will omit the equality sign. Okay? So we will have x minus 1 greater than 0. And this will follow that x is greater than 1. Thus, the domain of this expression is the set of all x element of real numbers such that x is greater than 1. Okay, so I hope that is clear. Now let us consider another activity. So in this activity, we will compare the two groups of equations. So we have here two groups, Group A and Group B. So for Group A, we have three equations as well as for Group B. To remember, from our previous activity, the domain of an expression or equation is the set of real numbers of the variable for which every term or part of the expression or equation is defined in the set of real numbers. Okay, now take note for equation 1 here, x squared minus 1 equal to 0. If we will try to substitute any real number to the equation, the output will be still a real number, right? So therefore, for equation 1, the domain will be the set of real numbers. However, there are only some values in the domain of this equation that will make the equation true or that will satisfy the equation. Okay, so there are some values of the variable that are in the domain of the equation but do not satisfy the equation. That is, they do not make the equation true. Example, when x is equal to 0 for equation 1, this will become 0 squared minus 1, which is equal to negative 1, which is not true. Okay, so for x equal to 0, the equation will not hold. Okay? So there are some values in the domain that will not make the equation true. In fact, there are only two values in the domain that will make the equation true. And those are the values negative 1 and 1. If you will try to substitute 1 here, so this will become 1 square minus 1, that is equal to 0, right? And if we have negative 1 square minus 1, that will also be equal to 0. So therefore, the equation will only hold if the values of x are negative 1 or 1. Okay? Now let's try equation number 2. This one. X plus 7 quantity square equal to x squared plus 49. Take note, if we will try to substitute again any real numbers, the result of the expressions here or any term in the equation will be a real number, right? So therefore, the domain of the equation will be the set of real numbers. However, there is only one value of x here that will make the equation true, or that will satisfy the equation, and that is when x is equal to 0. If we will have 0 here, so this will become 0 plus 7, and that is 7. Quantity square, that is equal to 49. So we have 49 in our left side of the equation, and for the right side you will have 0 squared plus 49, and that will become 49. So we have 49 equal to 49. So the equation will only be true if the value of x is equal to 0. Okay? And for the last one, so observe that the equation or the expression on the left is defined only if the values of x are any real numbers except positive 2. Because when x is equal to positive 2, the denominator here will become 0. So 2 will be excluded in our domain. Okay? And observe also that this equation will only hold if the value of x is equal to 3. That is, if you are going to try to substitute 3 here, so that will become 3 squared, and that is 9, minus 4, so that will become 5, over 3 minus 2, that is 1, right? Equal to 2 times 3 minus 1. So we have 5 equal to 5. So the equation will only hold if x is equal to 5. Okay, so for the equations in group A, there are only some values in the domain of the equation that will satisfy the equation, or that will make the equation true. Okay? However, in our equations in group B, take note for the equation 1, x squared equal minus 1 is equal to this one. Why? Because if you are going to have the factored form of x squared minus 1, you will get this factors, right? So therefore, in this case, the two expressions are just equal, or they are equivalent expressions. So in that case, the equation will hold for all values of x in its domain. Okay? Now let's have the second one. X plus 7 quantity square, if you are going to expand this one, the result will be x squared plus 14x plus 49. So they are, again, equivalent expressions. So therefore, in this case, the equation will hold for all values of x in its domain. Okay? In the domain of the equation. For the third one, take note that the domain is the set of all real numbers except positive 2. Okay? And take note, x squared minus 4 is just equal to x plus 2 times x minus 2. Right? So we have over x minus 2 equal to x plus 2. In this case, x minus 2 will be cancelled out. So we will have x plus 2 equal to x plus 2. So in this case, the two expressions are just equivalent expressions as long as your x is not equal to 2. So in this case, for the equations in group B, the equation will hold for all values of x in the domain of the equation. So comparing the two equations here, for group A, there are only some. okay, values of x that will satisfy the equation, while for the equations in group B, all values of x will satisfy the given equations. Okay, so those are the um, differences of the two groups of equations here. Okay, so we have here types of equations. So from our previous activity, we have seen there the two groups of equations. Now for group B, that is what we call the identity. Okay, so what is an identity? So an identity is an equation that is true for all values of the variable in the domain of the equation, like the equations in group B. Okay, so those equations are actually identities. Okay, and the second type of equation is what we call the conditional equation. So what is a conditional equation? So this is an equation, so that is not an identity. Okay, so a conditional equation is an equation that is not an identity. That is, if some values of the variable in the domain of the equation do not satisfy the equation, then the equation is a conditional equation. In other words, there are only some values of the variable in the domain of the equation that will satisfy the equation. Okay? So here, we are going to determine whether the equation is an identity or a conditional equation. Okay, so let's have first this one. We have 1 plus x squared over 1 minus x equal to 1 over 1 minus x. So this one is actually an identity. Why? Because if we are going to simplify this expression here, okay, so the expression on the left hand side of our equation, this will just be equal to, so if we, so the LCD is 1 minus x, right? So 1 minus x. So we have 1 plus x, multiply it by 1 minus x, right? Plus x squared. Okay? And this will now be equal to 1 plus x times 1 minus x is 1 minus x squared plus x squared over 1 minus x. So this will become negative x squared plus x squared. That will be cancelled out. That will be 1 over 1 minus x. So the two um, expressions here in the left-hand side and the right-hand side of the equation are actually equivalent expressions. Hence, this equation is an identity. Okay, so this one is an identity. Okay, let's have number two. So cosine squared theta minus sine squared theta all over cosine theta plus sine theta is equal to cosine theta minus sine theta. So this one is again an identity. Why? So let us try to show. Take note that cosine squared theta is equal to cosine theta quantity squared. Okay, so they are just the same. Same goes with the other trigonometric functions. So in that case, this one here in our left-hand side of the equation will become cosine theta, okay, theta squared minus sine theta squared all over cosine theta plus sine theta, right? So from that, this the expression in our numerator is actually a difference of two squares, so we can factor this one. So we have cosine theta plus sine theta times cosine theta minus sine theta, right? All over cosine theta plus sine theta. So from that, this will be cancelled out. So we will have
cosine theta minus sine theta, which is this one. So therefore, this equation here is an identity. Okay, so number 2 is an identity. Now for number 3, we have tangent theta equal to cotangent theta. So in this case, we all know that tangent theta is not always equal to cotangent theta. So what are the values of theta that will make tangent theta equal to cotangent theta? Actually, if we have theta equal to pi over 4, tangent pi over 4 is equal to 1. Cotangent pi over 4 is equal to 1. So therefore, the equation here will hold, or the equation will become true if theta is equal to pi over 4. So in that case, this equation is not an identity but a conditional equation. So this one is a conditional equation. And for the last one, we have cosine squared x equal to 2 cosine x plus 3. So this one is not an identity. So therefore, this is a conditional equation. So this equation will not hold to all values of x in the domain of the equation. So you can check that one. So what are the values? So let us have one value that will make this equation true. Let's try x equal to to pi. So cosine squared pi, take note that cosine pi is negative 1. So therefore, we have negative 1 square. So that will become positive 1, right? That is when x is equal to pi. And 2 times cosine pi, again, cosine pi is negative 1. So 2 times negative 1, so that will become negative 2 plus 3, so that will become positive 1. So therefore, this equation will hold when x is equal to pi. Okay, and again, this equation is a conditional equation. So therefore, how are we going to check if the equation is an identity or a conditional equation? So what you are going to do is to check if the two expressions in the left-hand side of the equation and the right-hand side of equation, if you can write the left-hand side of the equation, okay, as an expression equal to the right-hand side of the equation. So therefore, if that's the case, your equation is an identity. If not, that will become a conditional equation. Okay? So that's it for the identity and for the conditional equation. And for our main topic for this lesson, we are going to discuss the fundamental trigonometric identities. So we will focus on the fundamental trigonometric identities. And the first one is the reciprocal identities. So what are the reciprocal identities? So we have the following. The first one is this one. Cosine theta is equal to 1 over sine theta. We already know this one. Okay? We also have secant theta is equal to 1 over cosine theta. And the last one, we have cotangent theta is equal to 1 over tangent theta. So that is the reciprocal identities. Okay? The second fundamental trigonometric identities is the quotient identities. So we only have two. So the first one is this one. We already know this one also. Tangent theta is equal to sine theta over cosine theta. And cotangent theta is equal to cosine theta over sine theta. So just take note of these identities. Okay? Next one is the Pythagorean identities. We have three. The first one is this one. Sine squared theta plus cosine squared theta is equal to 1. So, saan to galing? This one came from our unit circle. Take note, in our unit circle, we have the formula x squared plus y squared equal to 1. And take note, x is just your cosine. So x will become cosine, so cosine theta squared, and that is just cosine squared theta. And y is just your sine theta, right? So therefore, sine theta squared, so we have sine squared theta equal to 1. Okay? So therefore, we have this first Pythagorean identity. The second Pythagorean identity is tangent squared theta plus 1 equal to secant squared theta. Where this identity came from? Actually, this identity is from the first identity lang. From this sine squared theta plus cosine squared theta equal to 1. If you are going to divide both sides by cosine squared theta, so this will become sine squared theta over cosine squared theta, right? Plus cosine squared theta over cosine squared theta equal to 1 over cosine squared theta, right? So from that, I can rewrite this one as sine theta over cosine theta squared plus this one is just 1 equal to, I can rewrite this one as 1 over cosine theta quantity squared. Now, sine theta over cosine theta from our quotient identity, this is just equal to tangent theta, right? And tangent theta squared is just tangent squared theta plus 1 equal to 1 over cosine theta is secant theta. And squaring that one, so we have secant squared theta. So we have the second identity. Okay? And the third identity is this one, 1 plus cotangent squared theta equal to cosecant squared theta. So this identity is again from the first identity lang. So if we are going to divide both sides by sine squared theta, we will have, so this one, try to divide both sides by sine squared theta. So we will have sine squared theta over sine squared theta plus cosine squared theta over sine squared theta equal to 1, right? So from that, this will become 1 plus, this is cosine squared theta over sine squared theta. So that is cosine over sine, that is just cotangent, right? And since we have squared there, we have cotangent squared theta equal to, so this is just 1 over sine squared theta pala. And 1 over sine is just cosecant theta, right? So we have cosecant squared theta, which is our third identity. Okay? So these are our three Pythagorean identities. Okay? So we have this one. And for the last identity, we have the even odd identities. So the first one is for sine. So we have negative sine theta is equal to sine negative theta. So this one, you can see this through the graph of sine x, y equal to sine x. So sine theta is an sine function is an odd function. So that's why we have this identity negative sine theta equal to sine negative theta. The second one is for cosine. So we have cosine theta is equal to cosine negative theta. Cosine function is an even function. That's why we have this identity cosine theta equal to cosine negative theta. And the third identity for even odd identities, we have for tangent. Tangent is also an even, no, an odd function. So, tangent is an odd function. So, the same lang yung identity niya sa sine. So, we have negative tangent theta equal to tangent negative theta. Or if you are going to check that one, negative tangent theta, we will have negative of um, sine theta over cosine theta, right? From our um, quotient identity. Now, negative sine theta from this identity here is just equal to sine negative theta, right? Over cosine theta is just equal to cosine negative theta from our identity here. So we have cosine negative theta. And sine over cosine is just equal to tangent of our angle is negative theta. So negative tangent theta is equal to tangent negative theta. Okay, so those are our four fundamental trigonometric identities. So the first one is the reciprocal identity. The second one is the quotient identity. Third one is the Pythagorean identity. And the fourth one is the even odd identities. Now, for us to easily remember or recall the fundamental trigonometric identities, we can actually use this hexagon. Okay, so this hexagon will help us construct the fundamental trigonometric identities, especially the first three identities, namely the reciprocal, quotient, and Pythagorean identities. Let us start with the reciprocal identities. You can see the reciprocal identities, okay, on the lines inside the hexagon. Okay, so we have these 6 lines here. Okay, now for this reciprocal identity, suppose let's start with secant x. Now, secant x is equal to 1 over cosine. So, therefore, from here, secant x is equal to 1 over cosine x. So, that is the pattern here. So, we have secant equals 1 over cosine x. Okay, the same way, we can have cosecant x is equal to 1 over sine x. So here our direction is straight. Okay, so it is straightforward. You cannot have cosecant equal to 1 then over cotangent. You cannot have that one. Okay, so our direction is a straight direction only. Okay, and we also have cotangent is equal to 1 over tangent x. Okay, so that is the way on how to look at the reciprocal identities using this hexagon. You can also have the reverse direction. Sine x is equal to 1 over cosecant. Okay, cosine x is equal to 1 over secant, and tangent x is equal to 1 over cotangent x. Okay, so that is for the reciprocal identity. Now, how about for the quotient identity? So for the quotient identity, we have tangent equals sine over cosine. So that is now our pattern. So quotient identities can be seen on the lines outside the hexagon or on the boundaries or the sides of the hexagon. Okay, so here tangent x is equal to, so we have this line here, sine x over, okay, we have another line here, cosine x. Okay, so our direction here is clockwise. Now, how about for cotangent x? Now, from our formula, cotangent x is equal to cosine over sine. So, we have here cotangent is equal to cosine x, then over sine x. Okay, thus, regardless of the direction, it could be clockwise or counterclockwise, you can have the quotient identities. Okay, so you can also have secant. Secant x is equal to cosecant x over cotangent x. Or cosecant x is equal to secant x over tangent x. You can also have sine x is equal to cosine x over cotangent x. Okay? Or you can have cosine x is equal to sine x over tangent x. Or sine x is equal to tangent over secant x. And so on. Okay, so regardless of the direction, you will have the quotient identities. Okay, now for the last one, we have the Pythagorean identities. Okay, so the Pythagorean identities can be seen in the inverted triangles here in our hexagon. So we have actually three inverted triangles here. The first one is this, second one, this one, and the third one, this one. So how are you going to construct the identities using these inverted triangles? So the pattern here is plus equals. So plus equals here. So you are going to add the two functions here, then equals the third function here below. So we have here, since Pythagorean identities, we have squares. So you will just add squares here. So tangent square, sine square, cosine square, cotangent square, cosecant square, and secant square. Okay? So we will have sine square x plus cosine square x is equal to 1. Okay? Tangent square x plus 1 is equal to secant square x. 1 plus cotangent square x is equal to cosecant square x. So those are the three Pythagorean identities. Okay? So that is how you are going to use this hexagon here in finding the fundamental trigonometric identities. Okay, so let us try to um, apply the trigonometric identities in simplifying the given trigonometric expressions here. So we have here four expressions. So first, let's have number one. Okay, for 1 plus tangent x over 1 plus cotangent x. Now, how are we going to know that the expression is already in simplest form? So, ganito yung makikita nyo. Simplest form siya if hindi siya fraction form, or if fraction form siya, dapat naka-reduced form siya. Okay? So one way to look that to simplify a given trigonometric expression is to transform all functions involved in the given expression to its sine or cosine form. Okay? So in this case, for number one, we will try to change tangent and cotangent to sine and cosine. Okay? So in this case, this will now be equal to 1 plus tangent is just from our quotient identity. That is just sine over cosine, right? So we have sine x over cosine x all over 1 plus cotangent x is just cosine over sine, right? So we have cosine x over sine x. Okay? So again, what we applied here is the quotient identity. Okay? Now, simplifying, let's combine the two expressions here. So this will now be equal to the LCD is cosine, right? So cosine x yung nasa denominator natin. So we will just multiply 1 and cosine. So we have cosine x. 1 times cosine is cosine x plus sine x, right? All over yung LCD naman nito is sine x. So we have sine x here. So 1 times sine x is just sine x plus cosine x. Okay? Now, dividing fractions, we will just copy the numerator. So we have cosine x plus sine x over cosine x. Okay? Multiply it by the reciprocal of the denominator. So we have sine x over sine x plus cosine x, right? Now take note, cosine x plus sine x is just the same as sine x plus cosine x. So this will now be canceled out. So what's left is sine x over cosine x. And what is sine x over cosine x? This is just equal to tangent x. So the simplest form of this expression is just tangent x. So our final answer will be tangent x. Okay, so I hope that is clear. Now let's try number 2. For number 2, since all of the functions here are in terms of sine and cosine na, so we will just combine the two terms here. So here, the LCD will be the product of the two denominators here. So we have 1 plus cosine theta times sine theta, right? So 1 plus cosine theta times sine theta divided by 1 plus cosine theta. What's left is sine theta, right? And multiply it by sine theta. So we will have sine squared theta, right? Plus this one, 1 plus cosine theta sine theta divided by sine theta. So this is just 1 plus cosine theta, right? Times this one. So this is 1 plus cosine theta square, right? Now let's try to expand this one. So we will have sine squared theta plus, so the expansion will be 1 plus 2 cosine theta plus cosine squared theta, right? So you try to expand that one, ito yung lalabas. All over 1 plus cosine theta times sine theta. Now take note from our Pythagorean identity, sine squared theta plus cosine squared theta is equal to 1. Therefore, sine squared theta here, ito, plus cosine squared theta, magiging 1 lang yan. So we will have 1 plus itong natira. 1 plus 2 cosine theta all over 1 plus cosine theta sine theta. Now, 1 plus 1 is just 2 plus 2 cosine theta all over copy again. 1 plus cosine theta sine theta. Now, 2 is common sa numerator, so we can factor out 2. So we have 2 times 1 plus cosine theta all over 1 plus cosine theta sine theta. 1 plus cosine theta, common sa numerator and denominator, that is just 1. So what's left now is 2 over sine theta. Take note that 1 over sine theta is just equal to cosecant theta. So I can just write this one as 2 times 1 over sine theta, right? And sine theta is cosecant theta, so we will have 2 cosecant theta. And this is now our final answer for number 2. Okay? So I hope that is clear. Okay. Now let's try number 3. For number 3, so let's try to write the functions here in terms of cosine and sine. Tangent is sine over cosine, so we have sine theta over cosine theta plus cotangent is cosine over sine, so we have cosine theta over sine theta all over secant theta is 1 over cosine theta, right? And cosecant is 1 over sine theta. There. Okay? So that is sine. Now, so let's change that one to sine. There. So from that, let's combine the two terms sa numerator. So the LCD is cosine times sine. So cosine theta, sine theta. Cosine theta, sine theta divided by cosine theta is just sine theta, right? Then multiply it by sine theta, so you have sine squared theta plus cosine theta, sine theta divided by sine theta is cosine theta. Multiply it by cosine theta, you have cosine squared theta all over 1 over cosine times sine, so you have cosine theta sine theta. Now, from our Pythagorean identity, sine squared theta plus cosine squared theta is just equal to 1. So you have 1 over cosine theta sine theta over 1 over cosine theta sine theta. So from that, since they are the same, this is just equal to 1. So the simplest form is just 1. So that is our answer for number 3. And for the last one, for number 4, let's try this one. So we have 1 over 1 plus tangent squared theta from our Pythagorean identity. 1 plus tangent is just secant, right? This is secant squared theta. So we have 1 over secant squared theta plus 1 over this one. 1 plus cotangent is just cosecant squared theta. So we have cosecant squared theta. Okay? And from that, take note, 1 over secant squared theta is just equal to cosine because the reciprocal of secant is cosine, right? So therefore, this one is just cosine squared theta plus 1 over cosecant. The reciprocal of cosecant is sine, right? So therefore, 1 over cosecant is just sine squared theta. And from our Pythagorean identity, this is just equal to 1. Okay? So for number 4, we also have 1. Okay? So that ends our lesson for the fundamental trigonometric identities.